Hey guys, so we are trying to understand the relation between two coordinate systems or two frames of references. Now in our previous discussion we saw that it is possible for us to show that two frames of references are inverse of one another without even knowing the relation between the bases that constitute these coordinate systems. So when we don't know how the basis of the two different coordinate systems are related, it is still possible for us to show that these two coordinate systems or these two frames of reference are inverse of one another. And in order to do so, what we essentially need to find is Jacobian, or the change in one frame of reference with respect to another, and we need to invert it. So this will give us two Jacobian matrices, and when we take the product of these two Jacobian matrices, it is possible for us to have an identity matrix. When the product of these two Jacobian matrices, which talks about the change in one frame of reference with respect to another frame of reference, when the product gives you an identity matrix, then it means that these two frames of references are inverse of one another. If it fails to give you an identity matrix, it is not the inverse of one another. Towards the end of the previous lecture, we saw that it is possible for us to conceive a frame of reference that will not be an inverse of another frame of reference. Meaning, when we have a frame of reference whose bases are not perpendicular to one another, then we saw that in such a case, the product of the corresponding Jacobian matrices will give us non-zero diagonal values. So ultimately, when we have non-zero diagonal values, so ultimately we would end up with a non-identity matrix. So it means the coordinate systems that rendered us this particular combination of Jacobian matrices are not inverse of one another. So when you have a coordinate system in which the bases are not perpendicular to one another, what it essentially means is change in one basis is influences the change in another basis. So unlike the orthogonal basis wherein the change in one basis is independent of another basis, when your system is non-orthogonal in nature, when your references are non-orthogonal in nature, the change in one basis will influence the change in another basis. So ultimately, your diagonal element will assume a non-zero value. So ultimately, the product of the Jacobian is going to be non-identity matrix. So it means your coordinate systems are not inverse of one another. Now, even though this is clear that it is possible for us to have coordinate systems that are not inverse of one another, considering the context we are in, considering the framework we are discussing, that is, we are interested in materials, we are interested in materials research, is it possible for us to have a frame of reference wherein the bases are not perpendicular to one another? It is rather a valid question to ask. We are talking about inverse relation, and one place wherein the inverse relation does not hold true is when we have a system with non-orthogonal basis. How relevant is the system with non-orthogonal basis to us who are dealing with materials? Turns out it is hugely relevant, because in addition to our cubic crystal system, it is also possible in a crystalline materials that atoms assume a position that reflect a different sort of a crystal system, which is often referred to as a triclinic crystal system. In addition to our cubic, tetragonal, and other crystal systems, where the octams, which can be used rather to represent the positions of the atoms in the crystalline material, there is this triclinic crystal system which can also be used, or which is also assumed by atoms when they arrange themselves regularly in the crystalline materials. And the coordinates or the references, the frames of these coordinate systems that are associated with the regular arrangement of the atoms, the frames or the coordinate systems that we rather use in a crystalline materials generally reflect the unit cell that represents the arrangement of the atoms. If you consider a cubic unit cell, a cubic arrangement of the atoms that represents the crystalline material, the corresponding frame of reference that we use to describe the material overlaps with the crystallographic axis that we use to describe the unit cell. If you have a single crystal of a material, and this crystalline material, the atoms of this crystalline material assume a cubic crystal system. Then when you take the unit cell of this crystalline material, the frame of reference that we choose generally overlaps with the crystallographic axis. So in the green, what you see here is the unit cell, and the red is the frame of reference that we choose. The frame of reference overlaps with the crystallographic axis of the unit cell. In case of triclinic systems, the angle between the crystallographic axis are not equal to 0. So that factor characterizes our triclinic unit cell. In case of triclinic systems, when you have a crystalline material wherein the atoms are arranged adopting the triclinic system, and when you take the unit cell of such a crystalline material, you would find the crystalline axis are not perpendicular to one another. So when you are dealing with such triclinic materials, the frames of reference of these triclinic materials are not inverse of one another. So this lack of inverse relation is also relevant to us because there are unit cell, there are ways we can arrange these atoms wherein the corresponding frames of references are not perpendicular to one another. So with that understanding, in this lecture what we will focus on is the way of expressing the matrices and the matrix multiplication. The reason is rather straightforward. So all this Jacobian matrix, coordinate system and their multiplication, we are considering it because we are interested in tensor, and we want to have a tensor that is independent of the frame of reference. So because we are interested in tensor, our starting point for all this discussion is tensor. So therefore, whenever we are dealing with tensor, we are going to involve matrix representation, and on top of it we are going to use matrix multiplication. So our tensor discussion, our calculations involving tensor is going to have so many matrix representation associated with them. So therefore, it will be easy for us to rather handle these expression if we had some notations involved in it. So that is essentially what we will focus in this lecture. So since our calculations involving tensor is going to have so many matrices in it, we want to come up with a notation that can help us in easily representing these matrices and this matrix multiplication particularly. To start off with, let us consider two generic frames of references and the Jacobian of the one of such frame of reference. So we start by considering two different frames of references, and we are now going to consider how one frame of reference is going to change with another and express it in the form of Jacobian J1. Now from this Jacobian J1 here, we will be able to isolate out what are the frames of reference that we are considering. So from this frame of Jacobian expression here, we can say that the frames of reference that we are considering are Z1 or Z1 depending on where you are from. So I'm from India, so I'll say Z1, Z2 and Z3. And the other frame of reference that we are considering is Z1 prime, Z2 prime and Z3 prime. So essentially what we have is, we have two frames of reference, Z1, Z2 and Z3, and Z1 prime, Z2 prime and Z3 prime. So we are considering the Jacobian between these two frames of reference. So in case of J1, we are considering how the Z1, Z2 and Z3 is changing with respect to the prime frames of reference. Now we can also have another Jacobian which tells us how the prime frames of references are changing with respect to the Z1, Z2 and Z3. Now when you consider the product of these two Jacobian, what you essentially, before solving it out, you create such a matrix like this, wherein each of these entry here indicates the corresponding product of the rows and columns. So we have two Jacobian, we want to find if these Jacobians are going to help us arrive at the identity matrix so as to prove if these two frames of reference are inverse of one another, and all these calculations are associated with tensor. So we want to come up with a notation to easily represent this matrix multiplication. So one starting point is that we are, instead of writing the product of this row and this column in this place, we are replacing or introducing a variable that indicates it. Now this J11, the entity J11 in the product matrix is the product of this row and this column here. So as you can see, this is multiplied with this, that contribute to the first term. this is multiplied to this, it contributes to the second term, and this guy is multiplied to this guy, it contributes to the third term. So this is how we are able to arrive at this entry in the product matrix. Now this can be extended to J12, J13, so on and so forth, ultimately ending up at J33. So we are taking the product of the Jacobian matrices, and these products we are representing it as 1, 1, 1, 2 based on the positions of these products in the product matrix. Now again, our goal is to come up with a notation that will help us express this easily. Now if you consider the expression here, the expression that indicate the entry at J11. So we are considering the expression that pertains to our value at this position of the product matrix. Now if you consider this expression here, the first thing we could notice is these terms, that is the lower left term and the upper right term. These terms, lower left and the upper right, the indices that pertain to the lower left and the upper right are identical to one another. So I'm considering the term or one entry in the product matrix. I consider the expanded version of it, the actual version of it, the actual product version of it, and I find that two indices, the lower left and the upper right, in each of these terms are identical. Not only for this entry, the same holds for all the entries. So I have 9 entries, and each of these 9 entries have 3 summation or 3 terms in them, and in each of these terms my lower left and the upper right are identical to one another. So I have 9 entries, and in all these 9 entries I have 3 terms in them, and in each of these 3 terms my lower left index and my upper right index are identical to one another. So this allows me to rewrite this summation of terms as something like this, because my lower left and my upper right terms are identical in each of these terms. It allows me to replace this with a variable, and I can use the summation sign here. Since this holds true for all the entries in the product matrix, I can rewrite all the entries in the product matrix using the summation sign here. Again, the lower left and the upper right indices are equal, so it means I can introduce a variable and then correspondingly have the summation sign before it. Now the first notation, the first shorthand notation that we can use in the context of vector calculation is that when I see identical indices in certain position of certain positions like that of lower left and the upper right, they are identical indices. In this context, it is safe for me to assume that this means summation, even though the summation is not explicitly mentioned. So the first convention is when I find two indices are identical in the context of the vector or tensor calculations, and it is explicitly stated that this notation is being used, then it is safe for me to assume that immediately when I see two identical indices, it is safe for me to assume that there is a summation sign before it. So what it essentially means by that is I can rewrite this term as this without the summation, because I use the notation, and this notation tells me, I use this tensor notation which tells me that when I find identical indices, then it means there is a summation before it, and the number of summations that it involves depends on the dimensions that we are considering, that we will consider, that we will look into later. But as things stand now, within the framework of tensor calculation, when I find identical indices, and it is stated that some tensor notation is used, we will get to the name of the tensor notation soon. So when it says that some tensor notation is used, it means that I see identical indices and it's stated that tensor notation is used, it means that there is a summation before it. So to get rid of the summation, we use this identical notation. So we say tensor notation is used, identical indices is available, so it means the summation is before that term. So before each of these expressions here, because there are identical indices, it means we have to assume the summation, which will generally not be included in an expression. So when I say I'm writing this using tensor notation, and when I find that there are identical indices involved, then I have to include, or I have to assume that there is a summation involved. Now let us go to, so essentially what I have done so far is, instead of writing these three terms, these three product terms individually, now all these three product terms are encompassed in this one term. So instead of writing these three product terms, I now just have one term. So this is one way of, rather we are expressing it in the short form. So instead of having three distinct terms, now we have one term that describes the three distinct terms. Now let us see if there is any other way for us to further reduce or further simplify this notation here. Now if you notice, as these indices are identical, these indices here, that is my upper left and the lower right, they are identical and they indicate my position in the product matrix. In addition to being identical, they indicate my position in the product matrix. So this position is, in this position my indices are identical, therefore these are identical. In this case the position is not identical, it is 1, 2, so my indices are not identical, but still the position is reflected in this indices here. So essentially my lower left, the one highlighted in red, my lower left and the upper right, they are identical in each of these terms. So they vary across the terms, but still they are identical within each of these terms. On the other hand, my upper left and the lower right, these terms, they are identical in all the three terms, all the three summation terms, and also they reflect my position in the product matrix. So these two terms, they are identical throughout this expression. They are identical throughout this expression. My 1, 2 is identical throughout this expression here, and in addition to that they indicate my position in the product matrix. So 1, 2. So in the same way I can see they are identical throughout the matrix, throughout the expression, and they indicate my position in the product matrix. So it becomes also possible for me to rather replace it with another set of indices. So I'm replacing these two indices that indicate my position in the product matrix using I and J. Earlier I introduced I, and this is within an expression. They are identical and they mean that there is a summation before this term. Now I'm considering upper left and the lower right. They are identical all through my expression, and they also, more importantly, talk about my position in the matrix. So ultimately all the indices in these all the indices in this expression here, all the four indices can be categorized into two. Once in the blue, they belong to a single expression. Once in the blue, they belong to a single expression here, and all that they mean is we are getting rid of our summation. So once in the blue, they belong to a specific expression, and all that they mean is they indicate there is a summation before this term. On the other hand, the ones highlighted in red, the indices highlighted in red, they pertain to different expressions. If I assume I to be 1, J to be 1, it pertains to this expression here. If I assume J to be 1, J to be 2, it pertains to this expression here. If I assume J to be 2 and I to be 3, it pertains to the expression corresponding to this entry here. If I assume my I to be 3 and J to be 1, it corresponds to my expression that pertains to this entry here. So essentially, the ones in blue talk about the summation terms, and I and J, they talk about different entries in my product matrix. So I can then rewrite all these entries, all the 9 entries, using just these terms here. So all the 9 entries I can write using just a single term here, wherein my I and J, that is this I and this j, they correspond to the position of my entry in the product matrix. And this I here just considers the summation I have to do within that position. So when my this I and j changes, I'm considering different position. When my I and j changes, I'm moving from one position to another. When these guys changes, I'm moving within a position. So correspondingly, these are referred to as the free variable. These are referred to as the ones that dictate the position that varies with the position of the entries in the product matrix. We refer to them as free variables. The ones that are confined to a given expression and just they talk about the summation of the terms, these are referred to as the dummy variables. So using the combination of free and the dummy variables, I will be able to express all the 9 entries of my product matrix. So when I want to move across my product entries of my product matrix, I will be changing my free variables. When I want to move across the different terms within an entry, I'll be changing my dummy variables. So using the combination of dummy variables and free variables, I will be able to represent all the 9 entries of my product matrix. So essentially, first notation helped me to get rid of, the first notation that we used helped us to get rid of the summations. The first notation we used helps us to get rid of the summation. So that was the contribution of our dummy variable here. So dummy variable helped us to get rid of the summation. The free variable now helps us to get across all the entries of the product matrix, depending on what variables does these dummy indices assume. Correspondingly, the position of the entries in the product matrix that we are considering also varies. So all the 9 terms here, using the combination of dummy and the free variables, can be expressed using this single representation here. So this way of writing the matrix within the framework of tensor calculation is called as Einstein's notation. So yeah, the same guy, famous guy whom we all have heard of at one point or the other. So this way of expressing the entries of a matrix using this simpler notation is what we refer to as the Einstein's notation. So using the Einstein's notation, we are now able to write the 9 entries of the product matrix using just a singular term. The dummy variables help us in expanding each of these entries by getting rid of the summation, whereas the free variable help us move across the different entries within the given matrix. Now with this we will wind up and we will consider some application of the Einstein notation in the subsequent lectures. Goodbye guys.